Does the number of cups of coffee you drink affect your GPA? Or can the hours of sleep predict how well you perform on an exam? These are questions about relationships between variables. Linear regression helps us model these relationships and even use them to predict outcomes. In this chapter, we learn how to build and interpret regression models to make predictions from data.
So now we look at the chapter in detail. The goal here is that we will try to use a random variable. Here we know RV here, X here. And the random variable X here is easy to know. You can control. To predict a random variable Y, which harder to know or control. So in example like 1011 here, the market research team, they interested in they try to predict the monthly sales Y based on the monthly online advertising X. So in this case, you can see that the monthly online advertising is something you can control. You can decide to add more money or spend less money for the advertising fee. And the monthly sales is something you cannot control. So if that's your research objective, and then you need to collect your data. And the empirical data will be the pairs of Xi and Yi. Right? So Xi will be online advertising, and Yi will be the amount you get back. And you have different period, right? And from that you can plot it, maybe using a scatter plot here, where the x-axis for the online advertising you spend, and here the for y-axis here will be for the monthly sale here. So each dot here just represent for a pair of data you collected. And at least from the scatter plot perspective here, you can see that you should we see a trend, right? There are a certain relationship between those two. So here are some terminologies we need to know when we study linear regression. Regression is a technique that helps us to study the relationship between a target random variable Y and a predictor random variable X. And we can make it more complicated, but at our level, just think about that's a simple scenario. You have a target Y and you have predictor X, okay, and you want to study the relationship between the two. And regression is a technique it can help you to do that. Here the target Y here we also call the response or the dependent random variable. And the predictor X we call also call the independent random variable. And linear regression, in short, we write LR for this lecture. You see LR, which means we say linear regression. So linear regression just a special case of regression, okay, where we just use the most simple form, the simplest form, y equal a plus bx, to study the relationship between x and y. We can have more complicated form, but for our level, we just look at this very basic form, which is you a line, a linear line, to try to understand the relationship between x and y. And here, let us recall the linear equation. I believe in your 7th grade, you learned that. Basically, we have a linear equation between two variables, x and y. If we have can establish the equation, right? Y equal b naught plus b1x. And where b naught and b1 are constants, and x is the independent variable, and y is the dependent variable. And here, we can represent them by a line, this relation by a line. And in this line, y equal b naught plus b1x here, the b naught we call intercept, and the b1 is the slope. So in this figure, we have two lines here, and y equal half x plus 2, and y equal negative x, right? Negative 1 times x plus 5 here. So here, we look at this example here. to understand better. You just recall, right? Cool. Because you already know it. In the plot here, the blue line here, it's represent the blue here, right? Y equal negative x plus 5. So in this case, yeah, B naught, the intercept will be 5, right? The intercept is something had not stick with the x. And the slope, which is the thing stick with the x. So yeah, B1 in this case will be negative 1. So you look at the relation here, right? If you write in this form, we can write this line by 5 plus negative 1 times x, right? So which means the slope here will be negative 1 and intercept 5. And as long as you have a linear relationship like this, right? And if we give you an x, you should be able to find a y, and vice versa, right? If you know an y, you can also find out an x. So for example, for this blue line here, if your x is 0, and basically if you at the time your y you block in the line, here you get the y 5. So basically it's just this point, right? 0, 5 here. X0, Y5. Say if your Y 0, and you can see that your X should be 5, which is this point, right? This point. I say if your Y 1 and you plug in, you should be able to find that your X will be, you flip these two, right? And your X will be 4, right? 4. So for the question for you is that so for example, if you look at the red line, right? What is the slope and intercept here? So red line, y equal half x plus 2, right? And the answer here, like you just rearrange by this fashion, right? B naught plus B1x here. So B naught is something not tied to x, which is a 2, which is your intercept. Intercept, the intercept. And the slope is something tied with x, right? Which is half here. And similarly, if I give you an x, right, you should be able to find the y too, or vice versa. So here's some properties. So the slope B1 is the amount of change in y when x increase and 1 unit. So if this is a meaning, right? How we interpret the slope, right? So when x increase 1 unit, the slope B1 tells us this amount of change in y. The larger of the B1 absolute value, the steeper of the line is. So if you use a slope, you take the absolute value. If you have a larger value, B with the slope, right? Absolute value, which means the line is steeper. A B1, a slope bigger than 0, corresponding to a line that rises from left to right. So you see that this red, right? It have the slope we have, which is bigger than 0. So your line will go to the direction right from left to right. And a slope basically vice versa, which means if you have slope less than 0, right? And you have a line which rise from right to left, right? So it's a blue line here. And the intercept B naught, basically it's just a value of y as an x equal 0. So you see that if your x equals 0, so your y equal B naught. So it also it gives us the meaning of the intercept. And this figure, it just tells us, so this thing is a y equal x here. And this is the yellow here is a case where you have the slope is, with the absolute value is small. And then the red one is the slope with absolute value big, large. So it's kind of steeper. So same thing, you can see that, right? Even in different direction in terms of rising, but you see that this line has a slope absolute value is 1, and this line half, and the blue line is steeper. The red line is more flat, right? Kind of flatter here. So this case, again, for the two lines we just saw, right? For the blue line, the slope is negative 1. So the meaning of this is that if you increase x 1 unit, right, y will decrease by 1 unit. And the line falls from left to right. the intercept be not equal 5, which means when x equals 0, y equals 5. And for the red line here, the slope is half, which means for every increase of 1 unit in x, the y will increase half. And positive, right? It's positive, which means your line rise from left to right, but gently, right? It's less steep than the blue line. And the intercept here is 2, so which means when x equals 0, y equals 2. So here we just put everything we just discussed in previous slide in a more formal slide here. So here we talk about the scatter plot. So basically the scatter plot is a very useful tool where it's used to depict the relative relationship between two random variables. So here each dot here will be a pair of xi and yi for the predictor and response. And here we have a scatter plot where we have the x is the average temperature and the y the number of visitors at the beach for 90 days. So you have 90 points here, each point corresponding to one average temperature of the day and number of the visitor. So see we see a trend, right? A hotter day we have more visitor. And it does make sense, right? It does make sense. So this is a trend, we see it here. And with your TI, actually you can also do this plot with your TI calculator by plugging your all x value in one list L1 and on y value in a list L2, and then you do start plot here. It will allow you to do this plot. But for sure, for when you process with your work, right, you need some other tool, which is at least Excel. Or maybe say eventually you can also use different software like Minitab, SPSS, or Python. So let us look at the example. Here, Brandon, he keeps track number of time, the time he works on homework each week, and the number of problem he is able to solve, which is y here. Construct the scatter plot using this data. So we have data table, the hours he worked, right, on homework each week, and the y, which is number of problems he can solve. Okay, so when he work 1 hour, he can solve 1 problem. He worked 2 hours, he can solve 3 problems. He worked 5 hours, 3 hours, he can solve 5 problems, and so on. Okay, so we have here 5 data points. So the question is that I construct a scatter plot, right? So basically here, you need to do is that you need to give the draw 2D coordinate, right? Where you have the x-axis for the hours of work, and the y-axis for the number of problem he solved, right? So here, for example, 1 hour, so 1 problem, 2 hours, so 3 problem. So the x here is 2, the y is 3, 3 hour, 5 problem, and so on. Okay, so this is a scatter plot we have. So here, from scatter plot, it gives us, it's translated the data from a table to a visualized way, and it's effective in a sense, at least from here you can see clearly the trend, right? The more hours you work on the problem, Brandon work on the problem, the more problems he will be able to solve, right? He able to solve, which it doesn't make sense, right? Doesn't make sense. So here we talk a little bit about the linear regression rationale. Here just to show you the rationale behind here. So say when you get a line, right? Basically y equal for head equal b naught plus b1 x here. Another point you can for each given x naught, you can always find a y naught here by plug in this equation. So that those y naught here will belong to the line. And the other time you will find the distance between the y naught and y naught hat. Okay, so y naught here is observed data. The y naught hat is the data predicted from the line. And you just keep doing that for all the data points, okay? And basically the line, the baseline, okay, the baseline will be the line will yield the error which is the smallest, okay. And this we call the least square method in statistics. For our level, we don't need to look too much detail about this, but if you go maybe at a 4,000 or 5,000 level, and then you should be able to get this, find out the line, okay. But here, like for us, we just need to look at this theorem we call the best fit line equation. So basically, like statistician, they show us that, okay, if you specify B0 and B1 in such a way, okay, which is B0 equal to a summation of y, and so then times summation of x squared, subtract summation of x squared, times summation of x y, and then divide by this denominator. And this, and if you specify B1 in such a way, and then this line will be the line closest to all the observed data, okay, observed data. And here we have some requirements to make this work, okay, to make this work. And the requirement here, we have a data random sample and quantitative data. And data show a good linear relation of x and y, and there are no outliers, okay. So there's some requirement before you would be able to use this theorem. So we look at an example for 10.1.4 here about the relationship between a drama score and science score. So here, psychology is interested in a relationship between science and drama scores for primary school students. And data are collected from 7 students as in the table here. And the question here is find the linear relationship, regression equation, LR, linear regression equation, when predicting a science score based on the drama score. So here, basically, like your x here will be the science score, and your y, your x will be a drama score, right? You want to predict the science score based on the drama score. So your x will be drama score, and y will be science score, okay? And we have the score here. This student has a drama score 21 and science 11. This student have a drama score 5 and science is 29, and so on, right? 15, 15, 11, 23. So when you read the problem, you should know what is your y, right? The y is the thing you try to predict, and the x is the thing you're going to use it to predict the y, right? So in this case, you check the requirement 4 star here by basically like the first step we do is that we will plot it, right? We plot all the data point here about drama score and science score here. And you can see that data here, random sample, right? Show pretty good linear relationship here. And there are nothing very strange here, okay? No outlier here. And from that, because of that, right? And then basically like you can find the regression equation by just plug in the formula here, which is B1 equal to N. So in this case, your N will be 7 because you have 7 students. Right? And you have like summation of xi, xy, right? So basically you do 21 times 11 plus 5 times 29 plus 15 times 15, and so on, right? So you go like this, and plus 12 times 13, so which is the first chunk here. And subtract summation of x times summation of y. So summation of x, which is everything here, right? 21 plus 5 plus 15 plus 11 plus 26 plus 28 plus 12. And here I just times summation of y here. And the denominator will be n, which is 7 times summation of x squared. So which is 21 squared plus 5 squared plus 15 squared plus so on, right? And subtract summation of x and then square, right? We have to be very careful here. So summation of x, which in this case 21 plus 5 plus 15 plus 11, and totally, and after we add up and we square. So if we do that and we plug in, we should be able to get this result here. and which give us like B1 equal to the slope for this relationship will be negative 0.55. And similarly, you can also find a B0, which is this 26.418. And here is our line, right? Linear, the best fit line here will be with the intercept is 26.1418 and slope is negative 0.55 here. So interesting thing here that we find that they are negative in some slope, right? So which means in this case, the interpretation of slope is that if you increase x1 unit, right, and then your y will increase the b1 unit, right? So in this case, if you increase your drama score 1 point, and your science score will increase negative 0.55, or it will go down 0.55 point, right? And here we see a negative relationship between science score and drama score. So the task calculation here kind of tedious. Okay, tedious. It has to be very careful. But there are good news. Where the good news here is that you can use the linear regression here, function here from your calculator. Okay, by follow the step, insert the x list in L1, y list in L2 here, and calculate. Okay, and it should give you the relation. Okay, the equation you want. Yes, for example, this equation, right? And here a remark. So if you want to get a complete output for linear regression, you also need to put diagnosis on by using this function. Okay, second year catalog. We will need that eventually because we're going to look at the coefficient correlation in next couple of slides. So let us go through this example by using the TI. Okay, the TI and see how it goes. So you have a drama score at 21, 5, 15, 11, 26, 28, and 12. So this should be in your X list, right? X list, which is the drama score. You and the science will be 11, 29, 15, 23, 17, 12, 13. It should be in your Y list, right? So we have to be very clear about that, okay? The Y list is the predict the thing you want to predict, and X list is the thing you're going to use to predict the Y list, right? And here we want to predict a science, right? Based on the drama score. So let us do it together, and then we see whether we can get to the same equation here, right? So in your TI calculator, you do it. Start here, calculate. You go number 4 here, linear regression here. You have X list and Y list, right? But we didn't have list so yet, right? So I need to do a list here. So go to edit here. So this one, which you put the X list, which is the drama score, which you have 21, you have 5, you have 15, you have 11, 26, 28, and then 12. So this is the drama score. And the corresponding science score include 11, 29, 15, 23, 17, 12, and 13, right? 13. 21, 5, 15, 11, 26, 28, 12. Let's check it again. 11, 29, 15, 23, 17, 12, 13. Okay, so now we do start here and calculate linear regression here. X list, which is RAM score L1, Y list, which is science score L2. That's it. Yep, exactly, right? Negative 5.5 for the A, which is the slope here, right? And 26.418, which is the intercept. If you round up 3, right? Exactly. So in this quiz, it's asked us, so we have the data in terms of the $1,000. Basically, like we have 1, 2, 3, 4, 5, 6, 7 data point, right? So this month, the company they spend like 1.7 thousand, which is $1,700, 1.7 thousand, and they get back $368,000. This month they spend 1.5 and they get back this much. This month they spend 2.8 thousand and they get 65,000 and so on, right? So on. So the first question is that find a linear relationship, right? A linear regression line predicting the amount of cells. So here will be your y, will be your y variable, and here will be your x variable, right? So the y is the cells and the x is the advertising. And a good practice is that, we check the condition, right, requirement. So data random sample, right? Data show good linear relationship here. So here, like we do have some plot here for the dot. And no outlier, so nothing unusual, extreme here, right? So from that, we can use the theorem. You can plug in by using the theorem, but I suggest we just better to go with the TI, okay? So first you will need to insert the X in X1, L1, right? So in this case, remember your X will be advertising, okay? 1.7, 1.5, 2.8, and so on. So let us do it together, 1.7. You will edit, right? So your L1, which is your X, 1.7, 1.5, oh, 2.8 by 1.3, 2.2, 1.3. Okay, 2.8. Phi 1.3, 2.2, and 1.3. Okay, so we have 7 observation here. 1.7, 1.5, 2.8. Phi 1.3, 2.2, 1.3. Okay. Then the cell will be 360A, 340, 665, 954, 331, 556, and 376. Okay. 36A, 340. So you have to make it sure it goes to the corresponding place, right? 368 corresponding to 1.7 thousand. 340, $340,000, $665,000, $954,000. It's a good month. 331, 556, and 376. Okay. 368, 340, 368, 340, 665, 954, 331. 64, 354, 331, 556, 376, Okay, so everything looks good to me. Then you go to start here and calculate here. And go to linear regression here. X is 1, Y is 2. And then calculate. Okay, so our equation Y will equal to 171.466x plus B, which is 125.835, if you keep 3, right? So the intercept is B is 125.834, and the slope is 17.465, okay? So from here, you can write out, right? Let me add a slide here. You can write out your linear equation, regression line, right? It will be y equal 171.466x and plus 125.835, okay? So here, if a store spends 1,600 for advertising, how much sales they expect to get back in return? So here, basically, like our task is that we just do some kind of prediction, right? A very basic prediction task. So if a store they spend $1,600, how much they get back? So with this equation here, it can help us to do this kind of prediction task. So, and remember, but here you have to pay very careful attention here, right? The unit here in $1,000. So which means like $1,600, which is also corresponding to 1.6, right? 1.6. So basically like X equal to 1.6, right? $1,000. And you can plug in and find the Y hat, which is 171,466 times 1.6 plus 125,835 here. Let's see what we get here. So you do a calculation, which is 171,466 times 1.6 and plus here 125,835, right? 835, which is the intercept here. So 400,000 and 180, right? 400,000, 180. You keep 3, okay? 181. But remember, it's in thousand, okay? 1,000 be dollar, okay? So this is how you can use a linear regression to perform a very basic prediction task, okay? And the linear regression equation here help you to do the prediction task. It comes from the linear regression technique, right? Linear regression technique, in which here from this theorem. We find a line close this to all the data point, and here the rationale of this method, okay? But this theorem will be the backbone, and it helps us to find this, and it helps the people who make the TI calculator, right, to program it and make it run when you plug in. So now we will look at the coefficient correlation R, okay? So for the sample linear coefficient correlation R, this measurement, it helps to measure the strength of the linear relationship between two random variables. And we have formula for that. It looks complicated, but basically like more or less it just, can be extended in this fashion, okay? N times of summation of x I y I go over all the sum, right? For each pair, and summation x times summation y and divide by the denominator specified here. Some properties about the linear coefficient correlation R. So linear correlation coefficient is a number between -1 and 1. We can prove that, okay? But again, it's not a scope for this class, so here we just admit as a fact, okay? We just use a fact. And when your R is less than 0, negative, another time we say X and Y, they negative correlate. And if your R is greater than 0, and we see X and Y have a positive correlate. And R equal 0, in this case, we say they have no correlate, no correlation here, okay? And other than, the strength here, it just tells us how strong the linear relationship between the two variables. So larger absolute value R means that the correlation is stronger, okay? It can go to either direction, right? So here, roughly speaking, how strong we call strong. So we call the two variables have a strong linear correlation if our R absolute from 0.7 to 1, okay? So in the case for 1, we call perfect correlation. So it can go either direction, negative correlation, which is X increase, Y decrease, and the positive correlation, which is X increase, Y increase, right? So you remember like the cell and the online advertising, right? They positive correlated. The more online advertising you spend, right, the more sale you get back, right? But here, like for the example of the drama and science score, right? They're negative, right? The higher the drama score, lower science, at least for the data set, right? And say if you would say like the two random variables they have a moderate correlation, correlate with if your R between 0.3 to 0.7, and we call it weak if from 0 to 0.3. Okay, so in this case you can see this this plot here, right? Perfect correlation, strong, weaker, weak, right, and no correlation, which is everything should go all different places, right? There's no trend, right, at all. Here another quantity we call the R square. You know what R square here? With R square here. So basically, like the R square here, actually we can show that for a simple linear regression. Okay, we can show that the R here, specified here, if we do square, okay, it can be rewritten by this, a term, which is y hat. Here y hat is a linear line. Subtract y square, y bar, and then square, and divide by the summation of y subtract y bar square. So this is the denominator here had a meaning. It just tells us the total variation of y. Okay, the total variation of y. And the numerator here is tell us like how much variation in y it can be explained by a linear relationship, okay, between y and x. You can see here you replace the y, right, by the y hat, which is the linear regression line. Linear regression line. So the R square here basically it just tells us the proportion of the variation in y can be explained by the linear relationship between x and y. So this is the explained part by the linear regression, right? And this is a total variation. And in practice, often we denote R square by big R square. We call R square here. And again, if we look back the sales and advertise problem, okay, and you use the formula, you can calculate R square. You can plug in by using the formula directly. Summation x times I, 368 plus times 17 plus this times this, and so on, and subtract this, right? And if you plug in carefully, you should be able to get 0.98. And if you do square, right, if you like 0.96 and 96%. So which means in this case, you can conclude that about 96% of the variation in sales can be explained by the linear relationship of online advertising and monthly sale. So which means like the online advertising, it is a very good predictor, right? To study the linear relationship between sale and online advertising. And the good news is that actually you don't need to plug in this formula because it's very tedious and you can make a mistake very easily, right? So you can also use a TI calculator. Second here, you go down here. Okay, so here, right? So enter. So after you do that, okay, and you go back to calculate and do linear regression. At this time, it should show us the complete output. So we have a complete output, okay? It includes everything, right? The linear regression equation, the R squared, and the R. So which is exactly what we got here. Right. So this is the R squared and R. And the linear regression equation, we did talk about that already. So we talked a little bit about the best predicted value in linear regression. So the ultimate goal of linear regression is to predict, right, the y given a value x. For some x naught here, given x naught here belong or close enough to the range of x. Okay. So in order to get a very, kind of a valid prediction, right? Yeah, x naught should belong to the range of the x you observe from the data are close enough. Okay. So basically in this case, when we look at the linear regression, right? We equation in the theorem 1011 here. There's some condition, right? There's some condition, okay, which is 4 star here. There's some requirements here. So in the case the requirement violated, okay, violated, and then basically like for sure you cannot use theorem. And at the time, the best predictive value of y for given x equal x naught, because you cannot use the theorem, right? So basically, like the best guess we use is just the average, right? Because we need to provide a guess evidence base, right? And the best guess, if you don't have the theorem work out, right? I think naturally people will just look at the average value of y bar. And when the requirement satisfied, then yeah, we just plug in like we did when we look at the sale at $1,600, right? So you just plug in the equation and to get the best predicted value. So we should pay close attention, okay, if the requirement meet or not, right? So here an example about a house price and house size. So here we have data collected from house size X, right, and house price Y. So people, they plan to use the house size to predict the house price, okay? And yeah, here from this data, it yield the Y bar equal $150,000. What is the best predicted house price for a 2,000 square feet house? If, okay, the sample data has the R, which is a linear coefficient, right? Linear coefficient correlation, right? Each R equal 0.15, and the regression equation is y hat a 9,160 plus 77x. And here another case where the sample data has an R equal 0.88, regression equation is y hat 9,000, the same, right? 9,116 plus 77x. And assume here like the data has linear good linear relationship is R greater than 0.7. So here one assumption we have additional information here. So from here, like basically like the idea here is that like we check the requirement, right? So in requirement, it requires one requirement. It requires the data show a good linear relationship, right? Which is requirement 2 here. So in this case, and basically from the data, right? give us like R equal 0.15, which is pretty low. And here they also say that we only had a good relationship. It's a linear relationship if R greater than 0.7, right? So because that's the case, so basically the linear relationship assumption not reasonable, not hold, right? And then because of, basically the second condition violated, so which means like the best predicted value we use, we won't use the equation at all. This is useless now, okay? We cannot use it. And we have to use the y bar as the best predicted value. So which means corresponding to this case. And for the second case, where your R is 0.88, which is greater than 0.7, which is a linear relationship reasonable. And basically, like the idea that like now the condition satisfied, and therefore we can use this regression equation here to make prediction. Sometimes because like this is the equation we use, right? And we want to predict the size of the price of the 2,000 square feet house, right? So you just plug in x equal 2,000, and it gives us 163 and $160,000 for this house size. So basically, like the message here that like you need to check the requirement, right, before you perform the prediction. If the requirement violated, and then the best predicted value you use is that y bar. And if it's satisfied, then you can use the linear regression line. And here's some common misuse of linear regression here. One often misuse people use the infer causality, okay, for large value R squared. We cannot use linear regression coefficient R squared, right, to do the causality. So a very common example, popular example is that like the drowning in ice cream cell, okay. So suppose like here, like for this example, right, you have the high linear regression coefficient here, about 0.8. So basically, there's some association between drowning and ice cream cell, right? But it doesn't mean, eating more ice cream, right? Increased ice cream cell will cause more drowning, right? And also like the second misuse that the people just blindly plug in, right? Blindly performing reaction without checking requirement are common sense, right? And they don't check the requirement, they don't check the common sense. So basically they say if you predict the ice cream cell, or use ice cream cell to predict the drowning, and it doesn't make sense, right? It doesn't make sense. You don't have a common sense here. And another common misuse is that like you predict a value that far outside the range of x. Okay, so other time it will be not robust. Okay, in order to make a good prediction, your x should be close and belong to close to the range of the data collected. So these are some common misuse. Study hours and grade. Here's the data. Used to study the relationship between study hours and grade on exam Y here. And find the linear regression equation when predicting Y using X here. And then find the linear coefficient R squared, and interpret the results, right? And find the predicted grade. If you study 7.5 hours, that's 100 hours. So there are three parts, right? The first part is using predict grade, use the hour study, right? So again, you can plug in your TI, plug in the grade of 92, 72, 90, and so on the X list, right? A1 list, right? And then the hours in the A1 list up to 20, 16, 18, 17, and so on. And the grade for the Y list, right, which is the L2 list. And then you perform the linear regression. And if you do that, correctly, and you have to be careful, okay? Make sure you check, double check, okay? Otherwise, if you give a wrong number, your equation will be wrong, right? Your output will be wrong, and it will destroy the whole problem, right? Y hat equal negative 6.432 plus 5185 x, okay? And you also will be able to get your R and R squared are this quantity. So in this case, you see the R is 1.929, which it belong to the strong, right? Here we see the absolute between 0.7 and 1, which is strong, right? And also we have, in this case, you can get your R squared, which is 86.2%, right? 0.862 or 86.2%. So basically, like the interpretation here will be 86.2% variation in grade can be explained by study hours. And it does make sense, right? Your grade depends a lot on how much you study, right? And then in part C, find the predicted grade if just studies 17.5 hours or 100 hours, okay? So 7.5 hours is a good value because it belongs to the range, right? You have the range from 14 to 20, you can see here, right? So 70.5, and you can predict which is this, you plug in, right? You predict it. But say what if you study 100 hours, right? So other time you can see that this is far beyond the range of the data. So no, you cannot do anything. You cannot predict it, right? You cannot predict, not available here. Because like it's far out of the range, far out of the range of X, right? But say if you just try to plug in anyway, you see your grade will be about 500 point, right? 24 point, which make no sense here. So this is one common misuse, which is the number 3 here, right? Number 3 here. So here, like the concept of interpolation and extrapolation here. So interpolation basically the process you predict inside of the observed X value in the data, so which is just corresponding to the 17.5 hour we just saw here. And extrapolation, which is the process predicting outside observed X value in the data, okay? So prediction values need to meet 2 criteria. Reasonable, which is the result makes sense, right, in the problem context. So in this case, the study out here, it doesn't make sense, right? You predict, right? And also like reliable, which is X value need to predict was within the range of the given X value in the data. So for example, like if you try to predict 100 hour anyway, and it will not reliable, it also not reasonable, right? But if you predict 17, it's reasonable, right? And it's reliable, right? Because reliable because this value belongs to the range, and reasonable because you see that it makes sense compared to the whole bank of data, right? So another example here, you study the exercise and a test score. So we here just assume that the assumption met. You collect data, minute study, and a test score. Okay, so you have a 4 observation here, and here the equation we already give you. So find the best the predicted test score, right? If you spend 42 minutes exercise. So in this case, the 42 minutes, right, is slightly outside the range. Yeah, so it's still okay to plug in, right? It's okay to plug in. So you plug in the 42 minutes, right, exercise, and you got the test score, right? Test score is this, right? 83.7. And you plug in the 28 minutes study, right, which it belongs to the range, and then you get a test score here. So you can see that you can predict the test score for the 42 minute study and 28. So the 28 is interpolation, and the 42 here is extrapolation. Okay, extrapolation. You predict outside the range, but slightly outside. It's not a really bad thing, right? It's still okay. So now the last part, I check the reasonable and reliable A and B. So in part A and part B, it does make sense, right? For the results. So both of them, we could say they are reasonable. Okay. But in terms reliable, so 28 is reliable, but maybe 42 is less reliable because it's outside the range. Okay, but both of them are reasonable, right? Reasonable. It's unlike the case when we look at the study hour, right? So this guy 100 is not reliable, it's not reasonable too, because you see, and this guy is reasonable and reliable. So we have data here where we have like in 1,000, year 1,000, there are about 30,000 pirates estimate, okay? 1,200, 25,000, and this much, and in 1,900, we have estimated about 1,000 pirates worldwide. And here the global temperature different compared to this year, okay? So for this data, basically you can see that if you plug in a calculator, okay, they have an R very high, okay, very strong. So we have a strong linear relationship, okay, very strong, about negative 0.97. But again, here you can see that we cannot do the causal inference, right? There this suggests virus cause global warming, right? So basically, it's just getting hotter and hotter compared to this year, right? So basically, we don't have the causal inference here. And also the second question, does it make sense to perform a linear regression study between X and Y? And for sure, you can see that, even you have this data, right? Yeah, but people won't buy if you use such a model, right? Because there are no reason to believe that, the pirate, right, can be a good predictor for number of pirate, be a good predictor for the temperature, right? So this is one famous example when where people they if you collect data randomly, we X the number of pirates, right, and Y is the global temperature, and you see kind of a high linear regression correlation, but it just doesn't tell you anything about a causal, or maybe if you have the intention to borrow the model to do the performance here in terms of linear regression, and people won't buy it, okay? So when you process linear regression, you have to be very careful. It has to make sense, right? Common sense. So here a bonus here, basically it just show us like the evolution from symbol linear regression to artificial intelligence, which is AI nowadays, right? So I believe most of us know what ChatGPT is, right? And different kind of AI tools now today. And the symbol linear regression is just the first building block, okay? And 200 years ago, they use it, right? For symbol linear regression. So here, like we have the very the first picture on the left hand side here, which we use like the error, right? To work in, right? To predict the amount of money you get, right? So it makes sense to do that, right? The more you work, the more money you get, right? But then eventually, like if you go to more advanced level, you will consider the problem we call multiple linear regression, which is you can use a degree, error, and an age. Okay, 3 factors here to predict the amount of money you can make. Okay, so it's more complicated. Your life will be more complicated, but it will be more accurate, right? It will be better model. And then like eventually, like with artificial intelligence, is that like instead of you use maybe 2 or 3 variable, right? In this case, to predict the y with the output here. Now what we do is that we will say, in this case, we try to use the weight and the height to predict the gender. Okay, so for example, your y is gender, male, female, and you use the weight and height to predict it. But say we can use multiple linear regression, right? So, x1, a weight plus b height, right, equal y, right, and plus c equal y. But some people they kind of think, okay, why don't we just try to mix weight and height to make maybe something we call h1, and we also mix weight and height, and you make something called h2 here, and then after that you do this kind of mixing, the first step here with the linear regression to make H1 and H2, and then we do one more linear regression, multiple linear regression, mix H1 and H2 to make a gender. Yeah, so this is a more complicated thing, right? And this is just what the AI do. Okay, so it's we call this is called a neural network. If you study deeper in the math, okay, statistics about the AI, you see basically like you have multiple prediction predictor here, and you merge some of them to make a layer. After that, you merge again to go to the second layer here. So this is we call the first layer, we call second, we call the third layer here, and you go again, go to 4 layer, and from the wall of 4 layer here, you know, you can even go further to make to the final predicted thing, predicted value. So it's just like, you know, the revolution of your brain, right? Maybe you can think this as a kind of your brain in when you are kindergarten level. The first ray, second ray, so it just get more and more sophisticated along the way you study, right? You know more, and it just getting more accurate eventually. So this is what happened with the cutting edge technology AI nowadays. And the first building block is just come from simple linear regression, like we learned in this class. And so thank you so much for your attention. And this also concluded the chapter 10.